We're back. Apologies everyone for the technical difficulties. We're talking about the ideal gas law and how through the equation of state we have the relationship between the pressure and volume of a gas to its temperature. So we have the pressure of a gas times its volume is equal to its temperature modified by the mass of the gas and the gas constant. Because the mass of the gas and the gas constants are constant for a given amount, we often write the equation of state as simply pressure times volume is proportional to the temperature. You recall from earlier studies that the density of a material is equal to the mass of that material divided by the volume of space it occupies. So by taking the volume relationship and inserting that into the equation of state, we can write the density of a gas as proportional to the pressure of the gas divided by its temperature. So here we can see that for a given pressure, a fixed pressure, we increase the temperature of the gas, we'll get a decrease in density. Alternatively, we can think of a fixed temperature, and if we increase the pressure on that volume, we'll get an increase in the density of that gas. What does this mean for the atmosphere? So we know that for the troposphere, both pressure and temperature decrease with altitude. But pressure decreases quicker with altitude than temperature. You'll recall from the earlier figures that pressure decreases at an exponential rate with altitude, whereas the decrease of temperature with altitude is linear. The result is that the density of the atmosphere decreases with altitude. So here on the y-axis we have the density of the atmosphere, x-axis we have altitude, and we can see that for the troposphere there's that decrease in density of the atmosphere with altitude. Right, so water exists in the atmosphere primarily as a gaseous state, so it's in the form of water vapor. The amount of water vapor per unit dry air is called the mixing ratio, and we use the mixing ratio as a way of quantifying the amount of water in the atmosphere. It's given as this Greek letter omega, as the ratio of the mass of water vapor in a given volume compared to the mass of dry air in that same volume, as the mass of water vapor is typically a lot less than the, maybe 2 orders of magnitude less than the mass of dry air in that same volume, so it has units of grams per kilogram. Mixing ratio is one of the quantities that are measured by a radiosonde, and here we have the same data from the Perth radiosonde you saw earlier. However, we're showing mixing ratio on the x-axis, with altitude on the y-axis. You can see the general decrease in mixing ratio with altitude, higher mixing ratios at the lower part of the atmosphere compared to very low at the top of the troposphere to 0 above about 12 kilometers. So what this says then is that most of the water in the atmosphere is in the troposphere, but more importantly, most of it's concentrating near the surface of the atmosphere. The surface of the troposphere. The surface. The contribution that water vapor makes to the total atmospheric pressure is called vapor pressure. We represent that as this letter E, vapor pressure. E is equal to some combination of the mixing ratio times atmospheric pressure. This constant, and it is a constant for your purposes, is simply the ratio of the molecular mass of water to the molecular mass of dry air, comprised of nitrogen, oxygen, argon. We can rearrange this equation to give us the mixing ratio as a function of saturation vapor pressure. So we can switch between the two, and this will be important for your prac later this week, where you'll be quantifying the amount of water in the air, and you'll be switching from mixing vapor pressure to mixing ratio. So how much water can the atmosphere hold? The answer is that it's a function of temperature. Warm air can hold more water vapor than cool air. Recall that picture we had earlier of a volume of gas, and a warm parcel has greater intermolecular spacing, so there's more room for water vapor to insert itself in the gaps between the air molecules. Cooler air, however, is denser, so there's less opportunity to squeeze as much water vapor into the gaps between the molecules. So what happens when a volume of air can't hold any more water? Well, that's when it gets to that point, the air is termed saturated. And that's where we see water transitioning from its gaseous form, water vapor, into liquid, precipitation or condensation. The vapor pressure at the point of saturation can be calculated as a function of the air temperature. This is known as the saturation vapor pressure. So saturation vapor pressure is a function of air temperature. It increases as air temperature increases. Because of the relationship between vapor pressure and mixing ratio, we can write the equivalent in terms of mixing ratio at saturation. So this is the amount of water that can be held by a volume of air before it condenses. So we talk about relative humidity as being a measure of the amount of vapor pressure in the air relative to how much that air could hold. So in terms of what we measure as our vapor pressure at a given air temperature, we compare that to how much could be held by that same volume of air at that temperature. Remember, that's the saturation, the maximum possible amount water that air can hold at that temperature. And because we express this as a percentage, we multiply the ratio by 100. In terms of mixing ratio, we measure for a given air parcel the amount of moisture in that air. We compare that to the amount that air could possibly hold, and the ratio of the two times 100 becomes the relative humidity. So these are all interchangeable. Warm air holds more water vapor than cool air. So consider equal volumes of water in two different volume containers. On the left, figure A, is an example where we have cool air. Remember, that's smaller volumes, and that same amount of water, so the volume of water fills up a particular space in that volume of air. This is what we might call high relative humidity, because there's not much space left to cram more water into this volume of air. However, if we go to a different volume, greater volume of air, this is an example where we've heated the air up, so it's expanded. All of a sudden, that same amount of water doesn't take up as much room. So we could pump in more water if we liked. So this is an example before this becomes full. And this is an example of low relative humidity. So why is the volume of the B greater than the volume of A? This comes down to what's called Charles' law. For a fixed volume, a fixed mass of gas, at constant pressure, volume is directly proportional to temperature. So you recall earlier we calculated that the density of a gas is proportional to the pressure divided by temperature. So if we keep the pressure fixed and we increase temperature, that leads to a decrease in density. Decrease in density means an increase in volume. What do we call air? when it reaches 100% relative humidity? Well, we call that saturated, but the temperature at which the air saturates is known as dew point temperature. That's the temperature we'll get water transitioning from gas into liquid. Temperature has to cool down for saturation to occur. Warm air has a higher dew point. Recall that plot of the saturation vapor pressure increasing with air temperature. Colder air has a lower dew point. When we reach dew point temperature, that's when we see things like mist, fog, dew, and eventually rain start to occur. So here's another illustration of radiosonde data. These are the same data from the Perth radiosonde showed earlier. On the left, we have the air temperature in grey, decreasing generally with air temperature, with altitude up to the tropopause, and then changing behaviour. Also plotted in black is the dew point temperature. That's the temperature at which you have to cool the air down before that air becomes saturated. So when the dew point temperature is close to air temperature, that means that air, that parcel of air, is near saturation. So the circle highlights where we'd expect there to be a high relative humidity. And on the right, we have exactly that. We've calculated from the radiosonde data the relative humidity as a function of altitude. And at the point where the dew point temperature is close to the air temperature, we can see we get 97, in this case, % relative humidity. Next, we'll talk about the composition of air, and I'll pause.